क्या समर्थ
So for all x with the PS equal for all the value of x in the domain, then it will it doesn't exist in the domain of that.
yeah, good. That means see, if whatever the elements present in the domain, then if the given predicate p of x is true for all the elements present in the domain, that means it is satisfies, then the universal quantification will be true. If there exists at least one element in the domain, for that element the given predicate is false, then the whole universal quantification, that is for all x px, will be said to be false. Okay, we'll see more about universal quantification and then we'll go to existential quantification. Okay. Why today only 31 students? Another class is going on?
No, sir.
Okay. Okay. So we have discussed all about universal quantification. See the last class note in the universal quantification, what is universal quantification, what is the notation, and some examples we have discussed in the last class. So we'll some points related to universal quantification. See, besides for all, that means we have used the word for all, for that is the universal quantifier. That means except for all, the universal quantification can be expressed in some other ways. This includes for every. Instead of using for all, one can use for every, all of. That is the same meaning, all of. You can use for each, the same meaning. You can use given any. You can also use for arbitrary. Like this. That means in a sentence, English sentence, for all is given. For all stands for universal quantification. So instead of for all, we can use some other phrase of English, that is for every, all of, for each, given any, for arbitrary. Arbitrary means it may be any. Any means for all. That means all these phrases can be used instead of for all. If the domain of a predicate consists of finite number of elements, such as let x1, x2, x3 up to xn. Say. Then that means the domain of a predicate contains finite number of elements or n number of elements, that is such as x1, x2 up to xn. Then the universal quantification, that is for all x, p of x. P of is any predicate is same as. Any idea? The domain contains finite number of elements. That means x may be x1, x2, x3 up to xn. Then what will be for all x, px? Okay, see. For all x, x may be x1, x2 up to xn. That will be, for all means that will be conjunction. That is, for all x, let x equal to x1. That is p of x1 and p of x2 and p of x3, like this, up to p of xn. That means the universal quantification that is equivalent to the conjunction of p of x1, p of x2 up to p of xn, when the domain contains finite number of elements, that is x1 to xn. That is one of the property. Let p of x, that is given, let's say we are taking the same example, x square less than 10, and the domain consists of positive integers not exceeding 4. What is the truth value of the universal quantification for all x, p of x? Then tell me, this will be true or false?
So false.
It will be false, because see, when universal quantification is false, if you are getting a point or element in the domain, for that particular element the given predicate is false, then the whole quantification or universal quantification will be false. That means, see, here the given predicate, that is x square less than 10, and the given domain D. What is the domain? Domain consists of
1, 2, 3, 4.
Yeah, positive integers not exceeding 4. That means up to 4. That means 1, 2, 3, and 4. That is the set containing elements 1, 2, 3, 4, which is finite. As it is finite, so we can use this formula. So when the universal domain contains finite number of elements, so we can write the quantification or universal quantification for all x, p of x is same, means that is equivalent, is same as conjunction p of 1, x1 is x1, x2, x3, x4, that is 1, 2, 3, 4. P of 1, p of 2, conjunction p of 3, conjunction p of 4. That means universal quantification will be true when this whole conjunction will be true. Then when it will be true? When all are true. P of 1, p of 2, p of 3, and p of 4, when all are true, then this conjunction will be true. This conjunction will be true, that is the same thing, quantification will be true. But now check that p of 1 is true or false?
So true.
P of 1 true, p of 2, p of 2, p of 3, all are true. But what will be p of 4? P of 4 is
False.
yeah, 16 less than 10, which is false. As this is false, that means this conjunction will be false. As this conjunction is false means the whole universal quantification will be false. It follows that the universal quantification for all x p of x, where p of x is x square less than 10, will be false. Okay, if the same example, if the domain contains 1, 2, 3, then what will the truth value of universal quantification?
Sir, true.
It will be true. That means if the domain contains 1, 2, 3, so p of 1 is true, p of 2 is also true, p of 3 is also true. That means for all the elements present in the domain, the given predicate is true. In that case, you can say the truth value of universal quantification will be true. Okay. Then we will go to another quantification, that is existential quantification. Okay. The existential quantification, always universal quantification and the existential quantification of a predicate p of x is the statement or proposition. What is that proposition? See, that is important. There exists an element in the given domain or in any domain such that p of x will be satisfied. The statement, there exists an element in the domain such that px will be satisfied. See, notation for existential quantification. This, there exists x p of x. This denotes for the existential quantification of the given predicate p of x. Here, there exists. What is this? This will be, what is called this? For all symbol, that is universal quantifier. There exists, that is existential quantifier. Quantifier and quantification are two different. There exists x along with that predicate p of x. That is the existential quantification. But there exists x or there exists. That is the existential quantifier. Okay. Then we'll see when this will be true and when this will be false. Existential quantification that is standard notation, there exists x p of x will be true if and only if. Then tell me when it will be true. See, it will happen, there exists x p of x. What is x? X is the element in the domain. Then when it will be true? See, universal is for all x p of x. It will be true, it will satisfy for all x. That means there exists will be true if P of x, that the predicate is true for at least one value of x in the domain. Very simple. That means whatever the given domain, in that domain, just find an element x, at least one element. For that element, P of x is true. Then you can say that there exists x, P of x will be true. Only one element is required. Then tell me when it will be false. When existential quantification will be false. If it is false for all the values, that means if there exist no such elements, for which the given predicate is true. Then the existential quantification, there exists x, P of x will be false. That means very simple. When if you are getting at least one element in the domain, for that element the given predicate is true, then the existential quantification will be true. If there exists no such element, the given predicate is true. That means that for all the elements in the domain, Px is false. That means there is no element in the domain such that the predicate is true. Then you can say that the existential quantification is false. Let P of x, I'm taking the same example, x greater than 10. In the domain consists of all real numbers. Then tell me what will be the truth value of there exists x, P of x. Then what is the truth value of the quantification? That is there exists x, P of x.
Sir, I guess it will be true because it is true for if we take 1 as x, then it is true for that.
No, if you take x equal to 1 greater than 10, that is false.
No. Just if we take 12 or 13.
Yeah, if you take 11, 12 more than that, then you are getting at least one element so that the Px is true. Then you can say that the existential quantification is true. That means your domain is important. Domain is set of all real numbers. That means here domain D is set of all real number. That is important, the domain. That is R. So you can check that if you take x equal to 11, 12, 13, 14, all for these type x, Px is true. That means if you check for x equal to let 12, P of 12, what will be P of 12? That is 12 greater than 10. That is true. So the existential quantification there exists x, P of x is true. Then tell me if the domain contains element 1, 2, 3, 4, 5, 6, then what will the truth value of there exists x, P of x?
It's a false.
Yeah. In that case, that will be false. That means the same example, if the domain. D that equal to given 1, 2, 3, 4, 5, 6 also maybe. And P of x is same P of x, that is x greater than 10. Then there exists x, P of x will be false or true? It will be false, because see that P of 1 is false, P of 2, all the P is false. That means there exists no element in the domain such that P of x is true. That means you can write there exists no such element in the domain for which Px is true. That means that for all the values of x in the domain, Px is false. In that case, you will use the existential quantification will be false. Okay. Like this universal quantification, instead of for all, we are using for every, for each. Like this, some similar words you can use instead of there exists. That means besides using there exists, we can also express the existential quantification statements. In other ways, such as you can use for some. There exists means there exists at least one. At least one, that means for some. You can use also same, that saying for at least one. That is the same meaning there exists. You can use there is only. There is. That means these are some similar words you can use in existential quantification instead of there exists. You can use there is for at least one, there exists at least one, or for some, like these words. These are the similar words for there exists. Okay. If the domain contains finite number of elements, such as elements are, let x1, x2 up to xn. We are considering these elements. Then the existential quantification, general notation, there exists x p of x. P of x is the predicate. Is same as to what? Same means that is equivalent. Same as means that the all the otherwise equivalent. Equivalent to. Any idea? See, there exists x. X may be x1, x2 up to xn. So in that case, universal will be true for all x. So it will be true if at least one. At least one. That means which connective will be?
Disjunction.
Yeah, that will be disjunction. So x contents are x1, x2 up to xn. That is same as disjunction. That will be p of x1 disjunction, p of x2 disjunction up to disjunction p of xn. So that existential quantification there exists as P of x, that is same as P of x1 disjunction of P of x1, P of x2 up to P of xn if the domain contains finite number of elements. But in case of universal quantification, that will be conjunction. Okay. Take the same example. Let P of x that be the statement given x square greater than 10 and the domain or instead of domain you can use the word universe of discourse. That is the other word for domain. Universe of discourse, that is the same meaning as domain. Domain consists of positive integers not exceeding 5. What is the truth value of existential quantification? There exists x P of x.
True.
Yeah, it will be true or false?
So true.
Yeah, it will be true. We can use that property. Why it will be true? So according to question, what will be domain? Domain will be containing elements not exceeding 5. That means contains 1, 2, 3, 4, 5. That is the domain. And that predicate P of x, that is given x square greater than 10. Okay. Then the proposition or the quantification, that is there exists x P of x is equivalent to or same as what? This existential quantification will be same as to what?
So P of 1 disjunction P of 2.
Yeah, P of 1 disjunction P of 2 disjunction P of 3 disjunction P of 4 disjunction P of 5. So this existential quantification will be true when if this disjunction will be true. When this disjunction will be true, that means not all are true required. If at least one of them is true, then this disjunction will be true. This disjunction will be true as it is equivalent. That means that existential quantification will be true. So check that P of 1, 2, 3 all are false, but P of 4 is true. P of 5 is also true. Here P of 4, that is 16 greater than 10 is true. Also you can take P of 5, that is 25 greater than 10 is also true. You can also use that. That means if you are getting any one of P of 1, 2, 3, 4, 5, if any one of them true, then the existential quantification is true. It follows that there exists x P of x. It's okay. Quantifiers with restricted domain. Okay, see. As far we have studied, all the domains are finite set or it is set of real numbers, set of integers. So now we are going to restrict the domain. we are taking some conditions that the variable satisfies. We will take some conditions that will apply to the whole domain. Okay, we'll see. An abbreviated form or notation is used to restrict the domain. That means domain is let's set of real numbers, set of integers. We are going to adding some extra conditions to that domain. Restrict the domain of a quantifier. In this notation, what type of notation? We will add a condition. A condition that the variable must satisfy. Is added or included after the quantifier. After the quantifier. So quantifier is for all. Then there exist two quantifiers. So after the quantifier, we will apply some extra conditions. That condition means some expressions that the variable must satisfy. That variable may be x, y, z. Some variable must satisfy some conditions. That condition is added after the quantifier. These type of expressions are called quantifiers or quantification using restricted domain. Okay, we'll see. Yeah. For all, that is the universal quantifier. After that, I am adding x less than 0, x square greater than 0. Is an example of what? Which quantification or which quantifier? That is universal quantifier. Is an example of universal quantifier. With restricted domain. Where the domain is the set of all real numbers. That means see, the domain is set of all real numbers. But this is given that for x is all real numbers, but x less than 0 such that x square greater than 0. That is given. Then we can meaning that this statement that is given for all x less than 0, x square greater than 0. This means for all x less than 0, x square greater than 0. That means for every x is what? X is any real number. So for every real number x with
Sir, x is negative real number, right?
Yeah, x is negative real number. Good. So for every negative, you can write for every negative real number x. Or we are writing for every real number x with less than x less than 0, then x square will be less than 0. That is the same thing. That is the same thing you can write in other way. See, x square greater than 0. Where x is negative, so x is real number. That means what? use this statement in an English sentence. What will be the English sentence? You can write the square of a negative real number is positive, x square greater than 0. That means x square is positive, x is what? X is any real number. Every real number or any real number. So square of a real number is positive when that real number must be negative. That means you can use this, the square of a real number. You can write x is negative, so negative real number. The square of a negative real number is greater than 0. That means it's positive. That is the same meaning. This statement is also equivalent. Statement is equivalent to or same as. What? Any idea? Okay, see. For all x, okay. For all x, we have written x less than 0, x square greater than 0. That means the square root of negative real number is positive. That means x square will be positive when x is negative. Then what will be this? That will be a conditional statement, x square greater than 0 when x less than 0. That is the same meaning. If x less than 0, then x square greater than 0. Okay.
So in the second point, sir, how x square is less than 0, sir?
Yes, yes.
Sir, in the second point, sir, you have written x is less than 0, then x square is less than 0.
No, this same meaning that for all x less than 0, we are getting x square greater than 0.
No, sir, this no, sir, second point, sir. This statement for all x is less than 0.
Yeah, this statement states that for every real number x. So we have given that the domain is set of all real numbers. So for all, so instead of for all, we can use for every. For every x, x means x is a real number. So for every real number x that is given x less than 0, then we'll get that x square will be negative or x square less than, oh, I have written less than, no, that will be greater than 0. Oh, that is by mistake, a good thing. That will be x square greater than 0. Okay. You are saying that one?
Yes, sir.
Yeah, that will be x square greater than 0, not less than 0, that is greater than. Okay, good. Okay, we'll take one more example. There exists z greater than 0. Z square equal to 2. This statement is an example of what? Example of there exists, that means existential quantifier. Existential quantifier with some restricted domain. But the domain is given. The domain is the set of real numbers. Then we will simplify this statement. Then tell me this statement says what? Okay. I'm writing this statement. And in the given statement, there exists z greater than 0 such that z square will be equal to 2. This the same means that or states that what there exists. You can also there exists z greater than 0. That means there z is a real number. So there exists a real number. Z with z will be positive. such that z square will be equal to 2. Then tell me, in one sentence, what will be represent this? There exists z greater than 0, such that z square will be equal to 2. Any idea? In one sentence, representing there exists, yeah. That means see,
Z is equal to
yeah, z square equal to 2. What will be z? Z will be square root of 2. That may be plus, that may be minus, but it is given that z will be positive. That means that will be positive square root. That means you can write there is a positive square root of 2. That is the same meaning. That is, you can use the sentence there is a positive square root of 2. That is the same meaning. Also, the given statement or this statement is same as or equivalent to what? Any idea? See, there exists z. This the given statement that is same as or equivalent to there exists z. Z is positive as well as z square equal to 2. That means the given statement there exists z, that will be same as there exists z, z is positive and z square equal to 2. Okay. But in case of for all, that is the conditional statement. But in case of there exists, that meaning is there exists z, z greater than 0 and z square equal to 2. Okay. Binding variables. Okay, see. The type of statements containing quantifiers and the predicate. We'll see after the quantifier, we are using the variables always. For all x, there exists x, or there exists z. For all y, so all the variables x, y, z, whatever the variable used in the quantification. So there are types of variables. One type is bound variable, one is free variable. So what are free variable and what are bound variable? That are called binding variables. We'll see. When a quantifier is used on a variable x, let the variable is x, then we can say that this occurrence of variable or presence of variable is bound. That means this, when we are using for all x, there exists x. So after a variable, after a quantifier, a variable is used. So those variables are called bound variables. Those variables are used after a quantifier. Then these variables are called bound variable. Then another variable is free variable, that is called an occurrence of a variable. Occurrence means that is the presentation of variable. Variable which is not bound or not bounded by a quantifier. That means those variables which are not used or not written after a quantifier or not bound by a quantifier, or set equal to a particular value. Not set is said to be free variable. That means those variables are present in the statement, but they are not used or not bounded by the quantifiers. Also, no particular value is assigned to that variable. Then those type of variables are called free variables. Those variables are used by a quantifier or bounded by a quantifier or written after a quantifier. Then these variables are called bound variables. Okay. The part of a logical expression to which or to that the quantifier is applied, that is called the scope of the quantifier. That scope. That means in a mathematical expression or logical expression, we'll find the part to which, that means the that universal quantification or existential quantification. So what are the quantifier? First find the quantifier. So there exists x for all x. So this applied to what? Applied to what expression? That expression is called the scope. Okay. There are three types. One is bound variable, one is free variable, and one is scope of quantifier. Okay. Consider the statement or proposition that is given for all x, p of x and q of x. That is given. For all x, p of x and q of x, that is the scope. Then in this statement, variable x is bound or free? Here the variable x is bound or free variable?
Sir, bound.
Bound, yes. Here the variable used, that is variable x, is bound by the universal quantifier. You can write for all x. See, in for all x, that means for all x, for all is used the quantifier. After that, x is written. So this variable x, that's said to be bound. Then what is the scope of the quantifier? See, the scope of the quantifier, that is that for all x is written each. What is the scope? See, for all x, that is applied to what? Which expression? P of x and q of x. So that expression is called the scope. That means scope of the quantifier, that is for all x. That means here for all x is applied to which expression or which logical expression? That logical expression, that's called the scope. That is P of x n q of x. Why? Because for all x is applied to which expression? This is applicable to what? Applicable to p of x and q of x. For that reason, the scope of the quantifier for all, that is p of x and q of x. That is the scope. We'll see one more example. Consider the statement that is there exists x plus y equal to 10. Then in this example, what are the variables x and y? Which variable is bound and which variable is free?
Sir,
Yeah.
Sir, x is bound and y is free.
Yeah, x is bound and y is free here.
sir, both are bound.
Why both are bound? Okay, we'll see. Okay, here the variable x is bound by the existential quantifier. Fire for all. Okay, but
Sir, existential quantifier for all.
yeah, or
Or
not?
there exists.
Yeah, that will be there exists. There exists, but the variable y here, y is said to be free variable because the variable y is not bound or not bounded by a quantifier. That means there exists x written, so that is not written all about y. So here y is free variable. That means there exists, after that there exists only x written. So x is bounded by the quantifier, that is there exists, but y is said to be free. X is bound. And also you can use also no value is assigned. You can see no value is assigned to y. Then what is the scope of the quantifier?
X plus y is equal to 10.
Yeah, x plus y equal to 10 is the scope of the quantifier. There exists x. Okay. Okay, in this example, just you will solve it. Consider the given statement that is given. There exists x, p of x, and q of x, disjunction for all x r of x. That is the given statement. So here variables are bound or not?
So bound.
Yeah, all the variables are bound. Okay. Then what about the scope? There are two quantifiers. One is existential quantifier, one is universal quantifier. So scope will be different. That means the scope of first quantifier, that is existential, that is there exists x, is what? And what is this? That is scope means there exists x applied to what? Applied to,
So P of X and Q of X.
yeah, P of x and Q of x. H there exists x is applied to only P of x and Q of x, not R of x. And also similarly, you can see the scope of the next quantifier, that is universal quantifier, scope of the second quantifier in the statement, that is universal quantification for all x is what? For all x is applied to
R of X.
R of x. The scope is R of x. H for all x is applied to R of x. So in a statement, there are more than one scope of the quantifiers. That depends upon the quantifier. In this statement, it contains two quantifiers. One is there exists, one is for all. So there will be two scopes. So all the variables are bound, because see here for all x applied to R of x, there exists x applied to this. So okay, it will take just 1 minute. So you can see in this example, H, the scope of the two quantifiers do not overlap to each other. So the given statement can be written using two different variables. X and Y as follows. That means you can use there exists x, P of x and Q of x, disjunction for all x R of x. Instead of writing for all x R of x, you can take also another variable for all y R of y. That will be same. Okay, we'll stop here. Okay, I will give the attendance to all.
Thank you, sir.